So, an ideal spring of unstretched length, 0.2 meters, is placed horizontally on a frictionless table. One end of the spring is fixed, and the other end is attached to a block of mass of 8 kilograms. The 8 kilogram block is also attached to a massless string that passes over a small frictionless pulley. A block of mass 4 kilograms hangs from the other end of the string. When this spring and block system is in equilibrium, the length of the spring is 0.25 meters, and the 4 kilogram block is 0.7 meters above the floor. Alright, to start out on part A, we are going to construct free body diagrams for the forces acting on each block when the system is in equilibrium. To start, we will begin with the 8 kilogram block. On the 8 kilogram block, the force of gravity will be acting on the block, and the normal force will be acting on the block in the opposite direction. Thirdly, the tension in the string will act on the block, and the force of the spring will act on the block in the opposite direction. Now for the 4 kilogram block, you will have the force of gravity and the tension of the string acting in the opposite direction. For part B, we are going to calculate the tension in the string. To do this, we are going to start with the simple equation force equals mass times gravity, gravity being the acceleration. In order to solve for the tension in the string, you can substitute tension in for the force. To solve for the tension, you will multiply the 4 kilogram mass by 10 meters per second squared, which is the acceleration due to Earth's gravity, 9.8 rounded to the nearest whole number. Multiply these together and you will reach 40 newtons. Alright, for part C, we are going to calculate the force constant of the spring. The ideal length of the spring is 0.2 meters, but at equilibrium, the length of the spring is 0.25 meters. This means that the change in length, x, will be 0.05 meters. In order to find the force constant of the spring, we will use Hooke's law equation of force equals kx. For the force, you can substitute the tension of the spring found in part B, which is 40 newtons, and for x, you can substitute the length that the spring is stretched, which would be 0.05 meters. In order to find the spring constant, you will divide the force by the distance the spring is stretched. 40 newtons divided by 0.05 meters. After dividing the two, you get 800 newtons per meter, which is the spring constant. Alright, so now the string is cut at point P. For part D, we are going to calculate the time taken for the 4 kilogram block to hit the floor. To do this, we are going to use the equation x equals 1/2 at squared. For x, we are going to substitute 0.7 meters, which is the distance the 4 kilogram block is from the floor. And for a, we are going to substitute 10, the force of gravity. In order to find the time it takes for the block to hit the floor, we will need to find the square root of 1.4, which is the distance the block is from the floor, multiplied by 2, divided by the force of gravity. After calculations, the time it takes for the 4 kilogram block to hit the floor is 0.37 seconds. Alright, for part E, we are going to calculate the frequency of oscillation of the 8 kilogram block. To do this, we must first find the period. In order to do that, we're going to use the equation T equals 2 pi times root m over k. For m, we will substitute 8 kilograms, which is the mass, and we will divide by the spring constant found earlier in part C, 800 newtons per meter. After calculations, you find that the period is 0.62 seconds. Now that we have the period, we can find the frequency using the equation. The frequency equals 1 over t, the period. Substitute in for the period. 1 divided by 0.62 seconds equals 1.6 hertz. Alright, for part F, we are going to calculate the maximum speed attained by the 8 kilogram block. To do this, we're going to set the expression for finding potential energy of a spring equal to the expression for finding kinetic energy, since energy is conserved within the system. In this case, the halves can be canceled out because they're on both sides of the equation. For K, we will substitute the spring constant, 800 newtons per meter, multiplied by the distance the spring is stretched, 0.05 meters squared. We will set that equal to the mass of 8 kilograms times velocity squared. In order to find the velocity first, we will need to divide the spring constant multiplied by the distance change in the spring squared by 8, and then in order to find velocity, we will need to find the square root of that entire quantity. After calculations, the maximum speed attained by the 8 kilogram block comes out to be 0.5 meters per second.